In today's session we will be discussing about basic flip-flops descriptors. Okay, how do you define a flip-flop? At the same time, what are all the present inputs, present outputs, next output, and some characteristic table, characteristic equation that defines the next state of flip-flop. Okay, at the same time, state transition, something like that we will be discussing in this session. So look at this. So for most of the use in analysis, especially circuit analysis or maybe digital circuit analysis, we require two concepts. Okay, what is the given circuit, whether it is a flip-flop or sequential circuit with a flip-flop, and what is the given state of the flip-flop, what is the possible next state of the flip-flop. Okay, all these things are defined by one table called as characteristic table. Okay, that defines, characteristic table is a table that defines the next state of flip-flop in terms of its inputs and current state. Characteristics table or characteristic table will define the next state of flip-flop in terms of its inputs, okay, and current state. In terms of its input and current state. Characteristic equation, which defines the next state of flip-flop as a Boolean function of the flip-flop and its inputs and the current state. Okay, so characteristic table will define its next state. At the same time, characteristic equation also will define its next state based on the current inputs. Okay, based on the current inputs and current state. Okay, so especially what is used in design, that is in designing any flip-flop or any digital circuit in a large quantity, we have to define the state transitions, how it will create a transition itself, okay, from one state to another state, right, from one state to another state, which is basically used in order to initially design the digital circuit. Okay, for this we require a table called as excitation table. We are exciting the flip-flop. Okay, we are exciting the flip-flop using this table, which defines the flip-flop's inputs that give a specific or specified present to the next output transition. It will tell you what input will create what transition. This is called as excitation table. Okay, I repeat. Okay, coming to SR flip-flop. Okay, coming to SR flip-flop, since these two are the inputs, S and R, Q of t plus 1 is the next state, t plus 1 state. Okay, t plus 1 state, when you are providing 0 0 for SR flip-flop, there won't be any change. It will remain in its same state. Okay, it won't change its state. Similarly, 0 1 will result in a t plus 1 state called as 0, which is called as a reset. Okay, in previous case it is called as a no change state. In 1 0 it will provide you an output which is called as set. Okay, which is called as set. Similarly, when you are providing 1 1, okay, it is an undefined state or unknown state, right? For the given flip-flop, which is SR flip-flop, the characteristic equation, that is Q of t plus 1, is given by S plus R complement into Q. Okay, R complement into Q. Q is your previous state. Q is, or Q of t is your previous state, right? This is the characteristic equation. Q of t plus 1 will be given by the equation S plus R complement into Q, whereas the excitation table, okay, excitation table is given by Q of t plus 1 and SR. What is the operation? Okay, these are the outputs. Okay, these are outputs, these are inputs. For this particular input, what is the output? That is I mean, that is called as your excitation table. In excitation table you will write it in that fashion, right? Excitation table you have, it's an output driven table. Okay, no doubt it's a output driven table. That means your outputs will define your inputs. Okay, excitation is nothing but what excitation or what input will yield what output. That is what the excitation is. Okay, just imagine your bike. If you raise your accelerator, there is a possibility of moving forward of your bike or a scooter. Okay, so it is an output driven, right? When you raise it more, the better you raise, the better will be your movement. Similarly, in case of output driven circuits, which is mostly driven by your excitation table, have outputs as the primary thing, that is q of t, current state, and the t plus 1, the next state. Okay, so all are dependent on the input only. Okay, but it is output driven, right? That means 0 0 0 1 and 1 0 and 1 1, these are the combinations where you already know what inputs will yield what kind of outputs from the previous table itself. Okay, so for the present input, what is the next output that you can expect? Okay, this is what excitation table will provide you. Okay, next one, for a D flip flop, the characteristic table is D of t and q of, where q is the q of t plus 1, where q of t is the current state, t plus 1 is the next possible state. We have 0 0 and 1 1 as the set and reset state, because in it is more similar to your SR flip flop with the two states eliminated. This and this are eliminated. Either you have set or reset. Okay, so we have set or reset here. Similarly, the characteristic equation is given by q of t plus 1 is nothing but d of t. It's the same thing, right? Excitation table is given by q of t plus 1, 0 and 1. We have 0 and 1 as the output. Like this, for each flip flop you can define this excitation table and characteristic table and characteristic equation. These are the three important things for any typical flip flop, that is essential in order to start working with your state tables. Okay, in order to start working with your state tables. Similarly, for JK flip flop, we have same concept as that of your SR flip flop. Okay, so here we have J and K and 4 combinations, where it is directly given by q of t plus 1, where it is the next possible state, where 0 0 will yield q of t, 0 1 will yield 0, which is reset, 1 0 will yield 1, 1 1 will yield a complement of t plus 1. It's nothing but a complement state, which is a toggle state, right? And the characteristic equation is given from this table itself, which is q of t plus 1 is equal to jq complement plus k complement q. Okay, jq complement plus k complement q. So for this, if you check the excitation table, q of t and q of t plus 1 with a combination of 4, that is 0 0 0 1 1 0 and 1 1, you get different possible operations, that is no change state, set and reset. The last one is again a no change state. Okay, the first is 2 are unwanted states. Okay, unwanted state, right? Similarly, for a toggle flip flop, we have t and q of t plus 1 is equivalent to, that is whenever t is given by 0, which is an input driven, the output is q of t, and whenever it is 1 also, it is a complement of q of t. Okay, it's a complement of q of t, which is given as q of t complement, right? And the characteristic equation, that is for the next state, that is q of t plus 1, is given by d of t, which is equal to t XOR of q of t, t XOR of q of t. This is what that is given in this particular diagram. It is clearly given. So you have a clock here, okay, and you have a XOR gate which is taken for one input, it is taken as q. So q XOR of t it's nothing but the same thing, q XOR of t, or t XOR of q of t. Okay, similarly the excitation table is given by q of t plus 1 is equal to, whenever it is q of t it is 0, whenever it is q of t complement it is 1. Okay, that is what the toggle outputs characteristic equation and excitation table.